This is Dr. Sirisha, working as Associate Professor in Institute of Aeronautical Engineering College. Today we are going to discuss about balanced set trees known as AVL trees and insertion and deletion operations on the same. So what is an AVL tree? AVL tree is a balanced set tree where the balance factor of each and every node must be either -1, 0 or +1. Then what do you mean by balance factor? Balance factor is nothing but the difference between the height of left and right subtree. So the difference can be -1, 0 or 1. One thing I want to make it very clear that binary search trees have come from binary search trees basically. So balance, you can make a balance out of binary search trees only. Prominently saying a binary tree. When you put a constraint on a binary tree is nothing but a tree which must have only 2 children. So okay, let's go a step or upper, where a tree can have any number of children with a root, right? So there comes a binary tree. If you put a constraint that it must have only 2 children, then it is a binary tree. Then on binary tree, if you put a constraint that its a left child must be lesser or equal to the root, whereas the right child must be greater than the root, then binary search trees come into the picture. For example of this one, let me see. 1 is there. If I try to insert 2, it will definitely go as the right child. If I insert 3, I'm talking about an ascending order one. So 3 will be the right child. If I want to insert 4, further it is going to extend itself in the right direction. Whereas the left subtree of all the nodes will be empty. I'm talking about constructing a BST of a sorted list. The height in one direction is going to increase rapidly. When we try to store the disk kind of data using arrays or linked list, memory wastage will be heavy in order. So to overcome that, we put again a constraint on BSTs to make them AVL trees, also known as balanced binary search trees. So AVL trees, what they say is that to balance the height, they always say that please see that the height difference of left and right subtrees must be either -1, 0 or 1, so that the height of the binary tree is well balanced. So when we store the data in memory using either arrays or linked list, array memory wastage will be very, very less. So have a look at the picture which I have given over here. Coming to the root tree. When you come to the root tree, calculate the height of its left subtree. This is the left subtree. Its height will be 3. Coming to the height of its right subtree. This is the right subtree. And its height is 3. So the difference of these two is 0. So on head of it, I have given 0. Randomly, let's take one more example. Say 30. Okay, the height of its left subtree is 1. As it do not have any right subtree, so it will be 1 minus 0, resulting 1 on its head, right? So this is how we are going to calculate the balance factors. After each and every insertion or deletion, we have to check for the balance factors to check whether it is abiding to the property of AVL trees or not. Remember always, balanced binary search trees are binary search trees. They get inherited from them, right? So never ever miss the property of BST. Converting the data, inserting, deleting, whatever operation you want to do it, but don't miss that property. Okay? Let's see. To get hooked to the property of AVL, if any node violates the property with the balance factor, if it goes either -2 or 2 or something like that, have to bring it back to our AVL property, back to track. So using rotations we can, it's not that if some node violates, remove it. No. we can rotate the data. That means rotation is nothing but rearranging the data. Please keep this in mind, rearranging the data. We can rearrange the data using single rotation or double rotation. Okay, single rotation means rotating the subtree or the tree once towards left or right direction. So they are known as left rotation and right rotation respectively. Coming to double rotation, we have to take two steps. First of all, do the left and right rotation, right and left, right left rotation. So on which node we are going to perform these operations, I'll explain with the example one by one rotations. Have a look at it for the first one. Here there is a scenario of inserting 1, 2 and 3, right? So if I start with 1, as it is the only node, its balance factor will be obviously 0. When I try to insert 2, so the balance factor of 2 is 0 because it is a leaf node, and 1 will be 0 minus 1, which leads to minus 2. Now have a look at the balance factors of each and every node. Both the nodes do not violate the rule of AVL. Fine. Next, insert 3. When I insert 3, as 3 is a leaf node, its balance factor is 0. Coming to 2, it will be 0 minus 1, which is minus 1. Coming to 2, 1. There is no left child for 1. So its left subtree height will be 0. Whereas a right subtree height is 2. So the difference will be minus 2. Now 1 is violating the rule of AVL, right? So now please think in this direction from the point of view of 1. So from the point of view 1, it is thinking why I violated the rule. So because of whom? So the newly inserted element is 3. Now 1 is thinking I have violated, very good, because of 3. Now where is 3? 3 is being inserted in its right subtree and it is sitting as a right child. Am I right? So in the right subtree of 1, 3 is sitting as a right child. So because of that insertion, the right side weight is heavy for 1. So rotate it towards left. Very simple. Pull the head of 1 towards left. So when you are going to drag it towards left, 2 is going to raise its head and it will become the root, and 1 will come down as the left child of 2. Okay. So once you pull the head of 1, as it becomes the left of 2, this will be the resultant tree. Now calculate the balance factor of 4. So you'll get all zeros because it is a well balanced one. Please keep this in mind and have a look. Even after rotation, we didn't violate the property of BST. Left hand children are lesser than the root, right are greater than the root. Okay. So this is the story of single left rotation. Whenever there is more weight on the right, please rotate towards left. So the node which violates the rule of AVL, you have to rotate with that node in your hands. Okay. So the next one, reverse of that scenario which we have seen just now. So I'm going to start with 3. As it is the only node, balance factor is 0. Insert 2. As 2 is lesser than 3, I'm going to insert it in its left. Calculate the balance factors. 2 is a leaf node, so its balance factor will be 0. Coming to 3, its balance factor 1 minus 0, which is 1. It doesn't violate the rule of AVL. Everything is fine till now. The story is going very smoothly. Now the value 1 comes into the picture and 1 is inserted as the left of 2. Let's calculate the balance factors. 0 as 1 is a leaf node. Coming to 2, It's a right child, left is 1, right is 0, its balance factor is 1. Coming to 3, its left is 2, right is 0, so 2. Now you can see that 3 violated the rule of AVL. So let's start thinking from in point of view of 3. What 3 is thinking? 3 is thinking that I lost the balance because of whom? Because of 1. Why and where is it sitting? So 3 will think that in my left subtree, 1 is sitting as a left child. So the weight in on my left subtree is heavy. So it rotates itself towards right. So when 3 rotate itself towards right, 3 will become the right child of 2. 3 will become the right child of 2. So as you can see, the BST property is not violated anywhere. Okay. So have a look at this picture. Again, calculate the balance factors. Now it is balanced. So please keep this in mind. Whenever there is an imbalance situation at any node because of insertion in uh, left side being a left child or right side being a right child, you need only one rotation. A single rotation will complete the story, or it will bring back our unbalanced AVL tree to a balanced nature. Okay? All the scenarios will not be like this. What if something goes and sits in the left subtree as a right child or in the right subtree as a left child? So it's a mix and match cases. In those cases, we need double rotation. Let's have a look at these examples. Let's have a look at a left-right rotation. The scenario goes like this. So initially 3, as it is a root, balance factor is 0. Insert 1, it will settle as the left child. Balance factor of 1 is 0, whereas 3 is 1. Okay, now insert 2. So as it is 2 is less than 3, it will come to the left direction, but greater than 1 to the right. Calculate the balance factors once again. So balance factor of 2 is 0, 1 is minus 1, whereas 3 is 2. Now 3 violates the AVL property rules. So now 3 is thinking, why I violated? Because of who? So because of the newly entered one, right? Who is the newly entered one? 2. Where it is sitting. So in point of view of 3, in the left subtree as a right child, 2 is placed. Left subtree as a right child. So, okay, now you can see a mix and match. So now it is going to divide its rotations into 2 halves. One left rotation and one right rotation. Let's have a look. Left rotation, first one. Which node must be rotated towards the left? So, keep one point in mind. The node which got affected is our main point. Okay, and the head of its left subtree, which is 1, will be rotated towards left. Okay, so here 1 is the head of the left subtree of 3. So it will be pulled towards left. Once you pull it towards the left, 2 is going to raise its head and reach its position or the position of 1. So 1 is going to sit as the left child of 2. Now let's go to the second rotation, which is right rotation. So right rotation of the affected node, the node which got affected or violated the node, which is 3 in this scenario. So right rotating means pull it down. When you pull it down, 2 raises and the rotation completes. LR rotation gets completed. Now have a look at this picture. Even the intermediate results, no one violates the BST. Okay, so and another scenario, a case where I try to insert 1, 3 and 2. Okay, so if I insert 1, okay, balance factor is 0. If I insert 3, the balance factor of 3 will be 0, whereas 1 will be minus 1. Okay, no violation, nothing. Now, insertion of 2. When I insert 2, the balance factor of 2 will be 0, 3 will be 1, 1 will be minus 2, right? So 1 violated the property of AVL. So now let's think in view of 1. Why it violated the rule? Because 2 was inserted. Where 2 was inserted? In the right subtree, and it is sitting as a left child. In the right subtree, left child. So it is a combination. Now it is going to divide its rotations into 2 halves. One in the right, the other in the left. Right? So let's do these rotations. Similar as left-right rotation. Okay, in view of the violated node, who is heading the right subtree? 3. So as 3 is heading the right subtree, rotate it towards right. So okay, so when you pull 3 towards right, 2 is going to raise and 3 will become the right child of 2. Okay, second step, that is left rotation. Left rotate the affected one, or the node which have violated the, that is 1. Rotate it towards left. So when you rotate it, the rotations have completed. You have rotated in both the directions. Now you get a balanced. Okay, so have a look that even the intermediate result did not violate the BST property. Please make sure that with every insertion or deletion, you're not supposed to violate the BST property even at the intermediate stages also. Okay, so these are the 4 rotations. We have to keep only one thing in mind. First point is the node which got affected and the newly inserted or deleted node, because of which the violation has started, right? So these are the 4 rotations which are helpful in insertion and deletion in binary search trees. Okay, balanced binary search trees. Let's take an example. So by implementing the operations of an AVL tree, which is insertion and deletion, the complexities are order of log n each. Coming to the insertion of an AVL tree, let's construct it. Insertion and creation one and the same, guys. So I have taken a list and I'm going to construct it by inserting each and every element. Initially 63, the first value. As it is the only node, its balance factor is 0. Now 9, as I said, AVL is a BST first of all. 9 will go and sit as the left child. So as it is sitting as the left child, so the balance factors 0 and 1 of 9 and 63 respectively, no violation. Now insert 19. While inserting, what you have to look, you have to start from the root. 63, as 19 is lesser than 63, it will go to the left subtree. When compared with 9, 19 is greater, so 19 will sit as the right child of 9. Now calculate the balance factors. 63 violated. Now think in point of view of 63. Why it lost its balance? Because of 19, right? So where is it sitting? In the left subtree as a right child it is sitting. The wording itself tells you which rotation you have to adopt. LR rotation, left-right rotation you have to adopt. So left rotation of what? 9. So pull it down. When you pull it down, 19 is going to take the place of 9. Right? So I'll show the result. After the first rotation, first half rotation, let me make it very clear. First half rotation, rotating 9 towards left, the resultant will be like this. Now, the right rotation of the affected node, which is 63. Pull it down. When you pull it down, it becomes the right child of 19. So, by the end of the rotation, you got a balance. Right? So, next, let's start inserting the elements. In the next order, we get 27. So, 27 will be the left child of 63. Again, calculate the balance factors. No problem. 18. Calculate the balance factors. No problem. 108. Insert it and check the balance. No problem. 99. No problem. 81. The problem raises. 81. You can see that 3 nodes violated. Because of what? Because of inserting 81. Very good. So now you have to think whose problem you have to solve because of 81. Yeah, because of 81, the nearest node which got affected is 108. So you solve the problem of 108, you solve the problem of family. Okay, right. So now in view of 108, where is 81? In its left subtree as a left node. Am I right? So because of 81, the left side weight is heavy for 108. So pull it down towards right. One single rotation is enough, right? So go for a right rotation. So right rotation. So when you rotate it, this is the result. So again calculate the balance factors. 63 and 19 which lost their balance previously now gain their balance. Now the total family tree is balanced and this is how we are going to insert. Okay, while inserting, if more than one node gets imbalance or they violate the rule of AVL, you have to think in view of the newly inserted element. What is the element which lost its balance because of it and which is nearest to it? If you solve that problem, the problem of the remaining is also going to rectify. Okay, it will not be a problem. Okay, let's have a look at the deletion. Deletion will be as it is as we have seen in binary set trees. But we need to keep one thing in mind. After removing an element, calculate the balance factors. If it violates any rule of AVL, any node, I mean to say any node violates the rule of AVL, adopt one of the 4 rotations and make it right. Okay, so let's see an example for the same. So for example, this is the scenario we have seen just now. Okay. So what if I delete 81? If I delete 81, no problem. Have a look at the balance factors after removing 81. Okay. So no problem. Fine. In this resultant one, what if I remove 27? Have a look, guys. In this, I want to delete 27. Don't you think something is fishy? Even I feel the same. Yes. Problem has struck. So 63, it violated the rule. Why it violated the rule? Looking at the picture itself, you can see its right side weight is heavy. It doesn't have any children on the left, but on the right side, it is having 2 children. So simply by moving or pulling 63 down towards left, job is done. Yes, once you do left rotation, 99 is going to go to the top and the AVL tree is balanced. Let's do one more deletion. Okay, so let's me take the same and I'll remove 18 out of this. Previously, I have removed 27. I have shown you scenario. Okay, so if I remove 18, what will happen? If I remove 18, have a look. The root got imbalanced. Because on its left child, only one child is there. The height is 1. And coming to its right, its height is 1, 2, and 3. 3. So minus 2. So what happened? Its right side weight is very high when compared to the left. So pull it towards left. Now this is the end of the rotations, and you can see and calculate the balance factors. So now it is a balanced. There's only one thing you have to keep in mind. After deleting a node, what is the node which is nearest to the deleted node which got violated or which got imbalanced? So, keeping in view of that affected node, judge which rotation you want to take. Okay, and just pull it left or right, right? So, and thereby you are going to balance. Have a look. You can watch the video once again. At each and every point, we have never ever violated the rule of BSTs. Okay, so remember, a balanced binary search tree is a binary search tree first of all. Okay, so we are balancing the heights to reduce the wastage of memory when we store it in our main. Okay, to violate that, we are doing. Let's see the pros and cons of the same, where we can apply this concept of AVL trees, where the designing of any database where we need not insert the or delete the data more frequently, but we need to search the data frequently. Remember, where the number of search operations is more than insertion or deletion. Very short search time it will, because it is height balanced and it is a balanced binary search tree, because at each and every iterations you are going to cut half of the data of or the list, you can say half of the list in your search area. Okay, half of your time will be saved. So, and if it is a neatly sorted data, then it is very fine. The disadvantage, the basic disadvantage with AVL tree is, if your database needs insertions and deletions on a frequent basis, with every insertion and deletion, you have to rotate your database, right? You have to rotate the content in your database to make it a balanced tree. If it violates the conditions apply, if it violates, you have to rebalance it, which needs very, very huge time if the database is heavy, right? So AVL trees, as their height balanced trees, generally people adopt this concept of AVL trees when there are less number of insertions or deletions and more search operations. At times we see the scenarios where the database is fixed, it's a rigid, which doesn't accept new data or which doesn't lose any data. It is only used to access or to search for some data, right? For only access purpose. In that cases, AVL tree is the best tree. Okay, so and to overcome this drawback of rotations, we can go with the red black trees, which are a next version of AVL trees, which I'm going to cover in your next videos. Okay, thanks a lot.
Like, share and subscribe. Hit the bell icon for more updates.